Okay, now that we've covered the basics, let's talk about why do we even need subnetting? Let's look at an example. So here we have a network with a router and three switches that are all connected to each other, and then they're connected to a single interface on a router. For this example, we're going to use a class A network 10.0.0.0/8, which means that only the first octet represents the network portion and all the three other octets represent the host portion. That means that we can have 2 to the power of 24 different IP addresses. Now, I'm not going to populate all of the computers with IP addresses, but let's say they have something like this. And we're going to talk about an example when one of the computers sends a broadcast packet. So here we have a computer with an IP address of 10.0.0.70, and this PC is going to send a broadcast. So what happens next is this packet goes to the switch. Now, a general rule is that once a switch receives a broadcast packet, it will forward this packet to all of its ports except the port where it received the packet. So what we will see here is that this switch in the middle is going to get a packet, and then all of the other laptops in this switch's network are also going to receive this broadcast packet. Now, the middle switch is also going to forward the packet to all of its ports except back to the port where it received the packet. So this packet is next going to go to the router, the switch to the right, and all of the laptops in the middle switch's network. Now, the router is not going to forward the packet because routers generally do not forward broadcasts, but this switch is going to forward the packet to all of these PCs, to all of the PCs in its network, I should say. So in the end, these are all of the devices on this network that have received this broadcast. Now you may notice that it says security here, and this is a security concern. Generally, broadcast is an enemy of security because the way a network functions normally is that when a computer receives a packet that isn't meant for that computer, is going to drop it. But then if you install, for example, Wireshark or any other sniffing program on a computer, it is going to read all of the packets that it receives, even if that computer wasn't meant to be a destination of that packet. But enough of talking about problems, let's talk about solutions now. I'm going to suggest two solutions to this issue, and the issue is a too big network. So we want to segment this network into smaller parts. One way we can do that is using VLANs. VLAN stands for Virtual Local Area Network, and it's used to virtually separate different logical segments of a network. In this example, I used three VLANs, 10.0.1.0, 10.0.2.0, and 10.0.3.0. And these three networks are appropriately named VLAN 1, 2, and 3. You will notice that all of them are /24, which means that they all belong in different subnets. So this is one subnet, and then this is another subnet. And we know that by looking at their network portions. If two IP addresses have different network portions, that means that they are different subnets. So when you look at colors behind laptops, in the first network, we have 6 laptops in VLAN 1. In the second network, we have 2 laptops in VLAN 1. And then in the third network, we have 5 laptops in VLAN 1. So if one of these laptops, let's say this one, sends a broadcast packet, all of the green laptops or all of the laptops that belong to VLAN 1 are the only laptops that are going to receive that broadcast. So even if all of these other laptops are in the same network or are connected to the same switch, they're not going to get that broadcast because they belong to different networks, at least virtually. So that's what you get when using VLANs. Now, the second solution is going to be to physically separate these networks. So we're going to delete the links we have between these switches, and we're going to instead connect each switch to a separate interface on a router. Now, you can't have two or more interfaces on a router that belong in the same network. So if you want to have a topology such as this one, you will have to give each interface on a router an IP address that belongs to a different subnet. In this case, the first network or the green network is going to be 10.0.1.0/24. This is the network IP address. And then to the interface of that network, we're going to assign, for example, 10.0.1.1. People or network administrators usually assign either .1, .10, or .254, which is the last usable IP address in an IP range. But for example, let's say that we can give .1 to interfaces. So all of these interfaces can be .1 in the host portion, but then they're going to belong to different networks because their network portions are different. So let's say that the green network interface is going to be 10.0.1.1, and then the yellow network interface is going to be 10.0.2.1, and the blue network interface is going to be 10.0.3.1. Now, the computers or the laptops can have, for example, this one can have 10.0.1.10, and this one can have 10.0.2.10. It doesn't matter that their host parts are the same as long as the network portion is different. So technically, they belong in a different network or they belong to different networks. If that computer or this first computer in the green network sends a broadcast packet, the only devices that are going to receive that packet are going to be the green laptops and the interface, the first interface on our router.